The majority of American nuclear power reactors are light water reactors, which use uranium as fuel. Before uranium can be used as reactor fuel, however, the concentration of its fissionable isotope, uranium-235, must be increased from 0.71% by weight to 3.2%. This process, whereby the concentration of a particular isotope is increased, is called enrichment. Current plants, such as the gaseous diffusion plant at Oak Ridge, Tennessee, and enrichment plants planned for the future, cannot economically separate more than about 70% of the uranium-235 isotope from uranium. The other 30% is stored as waste, commonly referred to as tails. In other words, about 1/3 of the useful uranium-235 isotope is not being collected by present technology. At the Los Alamos Scientific Laboratory, scientists and engineers are developing a new technology that will permit the economic recovery of the remaining uranium-235, thereby converting what is now waste into nuclear fuel, a national resource. This new technology, Laser Isotope Separation, or LIS, grew out of laser research at Los Alamos. It uses lasers and photochemistry in conjunction with uranium hexafluoride, or UF6, and offers several important benefits. The process is highly efficient, uses small quantities of electrical power, requires a comparatively small plant. Unlike other concepts, no dedicated power plants and no dedicated manufacturing plants are required. The process, if it can be implemented in production plants, can save a great deal of money and therefore promises to be extremely profitable. In addition, since the power consumption is low and the plant size comparatively small, the LIS plant can easily be located near a UF6 supply to reduce shipping and handling costs, as well as to enhance travel safety considerations. The LIS process promises to be commercially successful. Independent economic assessments were conducted at both the Oak Ridge Gaseous Diffusion Plant and at the Los Alamos Scientific Laboratory, comparing the cost of operating an LIS plant to the cost of mining uranium. Studies predict a clear profit or savings of $380 million per year in operating an LIS plant over the present costs of mining uranium. The initial capital investment for an LIS tails enrichment plant is estimated to be $550 million. Our supply of natural uranium is finite. It has been projected that by the early part of the next century, the world's uranium reserves will be nearly exhausted, but a large and growing stockpile of tails already exists. Over 500 million kilograms of tails will have been produced by enrichment plants by the end of 1990. If all the remaining uranium-235 in this material were removed, the extracted uranium would provide sufficient nuclear fuel feed material for approximately 1,800 additional reactor years of operation. About 45 million kilograms of tails will be generated each year starting in 1990. At present, uranium is enriched by the mechanical method known as gaseous diffusion. In this process, a feed stream of uranium hexafluoride passes through a filter or barrier material, of which there are thousands. By maintaining a pressure drop across the barrier material, the lighter uranium-235 F6 molecules penetrate much faster than the heavier uranium-238 F6 molecules. Thousands of large compressors maintain the pressure drop and move the feed streams. Those molecules which do not penetrate the barrier material are recycled through the system. Eventually, the process produces enriched uranium. However, 30% of the useful uranium-235 isotope is not collected and is stored as waste, or tails. A second way to enrich uranium is the recently developed gas centrifuge process. In this process, uranium hexafluoride is whirled at high speeds through thousands of centrifuge units. Since they are heavier, more of the U-238F6 molecules migrate toward the outer walls of the centrifuge than do the lighter U-235F6 molecules. These molecules are then drawn off and recycled through the system as the feed streams continue. Like gaseous diffusion, gas centrifuge also requires thousands of modules in series to achieve enrichment. And like gaseous diffusion, only 2/3 of the uranium-235 isotope is collected. The remaining 1/3 is stored as tails. In the following animation sequence, we describe the Los Alamos technique for separating the remaining fissionable isotope of uranium U-235 from depleted uranium, or tails. However, we need to explain in a little more detail the composition of uranium hexafluoride. Uranium hexafluoride, UF6, is a gas that contains two molecules of interest, U-235F6 and U-238F6. U-235F6 consists of one uranium-235 atom chemically bonded to 6 fluorine atoms. U-238F6 consists of one uranium-238 atom also chemically bonded to 6 fluorine atoms. The U-235F6 molecule, when hit by a colliding molecule, undergoes molecular vibration at a specific frequency. U-238F6 molecules behave likewise, but vibrate at a different frequency. Each molecule keeps vibrating as long as collisions continue to occur. If the molecules are cooled drastically, say to -200 degrees centigrade, vibration stops. Now, by directing a laser beam tuned to the precise natural frequency of U-235F6, we selectively initiate vibration in only the molecule of interest, the U-235F6 molecule. The laser does not, however, induce vibration in the U-238F6 molecule because of its different natural frequency. In the Los Alamos Scientific Laboratory technique, the molecules of U-235F6 and U-238F6 are placed in a container along with an inert gas. At slightly greater than room temperature and atmospheric pressure, the mixture is also a gas. This gas mixture is then directed through a valve and nozzle where the gas expands rapidly. The rapid expansion causes the temperature to drop instantly to about -200 degrees centigrade, at which point molecular vibration essentially stops. The speed of the molecules through the system is approximately 5,000 feet per second. Through windows in the nozzle, laser beams emit photons into the flowing gas. 2 lasers are required. The first is an infrared laser, which selectively causes initial vibration in the U-235F6 molecules. The second is an ultraviolet laser, which further increases vibration until chemical dissociation takes place. Here we see it in close-up. The infrared laser, the ultraviolet laser. In other words, the chemical bond of one fluorine atom is broken, and the fluorine atom becomes a free atom. The key to the process is the formation of a new molecule through dissociation of a fluorine atom. This new molecule, U-235F5, which contains the important U-235 isotope, is a solid rather than a gas, as was the U-235F6. This solid U-235F5 impinges upon a plate where it can now be easily collected and recombined with fluorine atoms to form U-235F6. The detached fluorine atoms and the unwanted U-238F6 molecules flow on through the system. The efficiency of extraction could approach 100%. Here we see an actual experimental system. The nozzle, where expansion and cooling of the molecules takes place, is located downstream of the supply tank. The lasers in adjacent rooms selectively initiate vibration and dissociation. Compressors move the gas and enriched molecules to the collectors. In the summer of 1976, this small-scale experimental system was used to demonstrate the scientific feasibility of the LIS uranium enrichment process with the first collection of milligram amounts of slightly enriched uranium.
A tails enrichment plant, by definition, is designed not to enrich beyond the level of natural uranium. It would be extremely difficult to alter an operating tails enrichment plant to produce weapons-grade material because features are designed in the plant that tend to limit the enrichment to a specified value. The LIS process inherently carries a low risk of proliferation because it utilizes the most complex process and hardware available in the United States. In fact, several study groups have concluded that risk of proliferation with LIS is lower than with other planned enrichment processes.
Laser isotope separation technology also opens up the possibility of many new applications.
We all believe that these technologies that are being developed for laser isotope separation will prove very useful for a large number of other chemical processes. Processes in industrial chemistry, medical and biological applications, in the field of pharmaceuticals, for example. The laser allows a new tool to initiate chemical reactions, whereas if I mix together a number of reagents and apply heat to the system, I can produce chemical reactions. If I apply the laser to that same system, I can specify the products very exactly and thereby produce exactly what is desired for any given application.
The versatility of the Los Alamos laser isotope separation process permits several enrichment plant options. For example, enrichment plants could be designed as modules to enrich tails to natural uranium, as described in this film. Or the plant could be designed to enrich tails and natural uranium directly to reactor fuel, 3.2%. The latter option would release about 7,000 million watts of electrical power to our nation. Laser-induced chemistry is a new and exciting field. Scientists and engineers have barely scratched the surface, but already they see an almost limitless number of possibilities for practical applications.